right, thank you so much for having me. This has been a really wonderful event. Maybe a more honest title would be How to Do Research in Diffusion Models Without Ever Talking About Neural Networks, which I think is a very silly premise, but let's see what I could do. So on the same page, here's some setup. So we have some data distribution, which is the distribution from which we want to generate samples. And then what we do in diffusion models is we first run this data distribution forward in time through some stochastic process, which in this talk, since it's just mathematics, it'll be the simplest possible process, the Ornstein-Uhlenbeck process. Okay, and then PT will be the law along the forward process. So the stationary distribution of Ornstein-Uhlenbeck is standard Gaussian, so this takes all your data samples to pure noise. And then the fact from SDE theory is that SDEs can actually be reversed in time, and the time reversal is also an SDE. The time reversal of the forward process is written up here. So you notice that the drift changes sign from minus xt to plus xt, but more importantly, the drift, we add an extra term, which is the gradient of the log density along the forward process. This is called the Stein score, or just simply the score function in this talk. And now the reverse process is a generative model because it will take us from pure noise to hopefully samples from the data distribution. That's the idea behind diffusion models. Now, like in this reverse process, when we try to implement it, the issue is that we don't have access to the score functions. So what we do is we instead try to learn the score functions. I will talk about the learning of the score functions in the second half of the talk. But for the first half of the talk, I'm just going to assume that the score functions, we have some estimates of them that are given to us. Okay, so the question here is, given these estimates, how can we try to implement the reverse process? So the simplest possible discretization would be, well, maybe not the simplest, but a simple one is you just plug in the score function, the estimated score function into the true, in place of the true score function. Okay, and then you just freeze the nonlinear part and then integrate the rest because it's a linear SDE. So here, t with the subscript minus, this is supposed to be the discretization time step, like the largest multiple of the step size, which is less than time t. And we initialize this at the standard Gaussian, and then we run backwards to get to p hat 0. Okay, so in the first part of this talk, I'm just going to talk about guarantees for discretization of this process. So the kind of question we're interested in here is, if we know that the estimated scores are accurate to some level, then how does that translate into final error of getting samples from the data distribution? And also, like, how many iterations does it take, and so forth. So this part is actually mostly kind of a literature survey. Let me just start with the basic result, which was like done maybe 2 years ago now. So the basic result for diffusion models says that if you adopt these assumptions, you can get TV close to the true distribution with a number of steps, which is roughly L squared d over epsilon squared. So let's just try to parse this theorem a little bit. So first of all, the first bullet point, these are the assumptions on the data distribution. The first assumption is that the score function is Lipschitz along the forward process. Actually, like, you don't need to worry about this assumption because that assumption could also be dropped later, but we'll start with this assumption. And then the other assumption is that the data distribution is bounded second moment. Okay, so what I want to say about the assumptions on the data distribution are that there's practically none, because we will drop this Lipschitz assumption later. And that's interesting because typically when you consider sampling, you need to have some kind of assumption that the data distribution looks, let's say, like unimodal or close to unimodal. And the reason why is if you want to sample from such a distribution and you use a local Markov chain, if your distribution has many modes, you'll suffer from this like slow mixing going between modes. And then there's other more sophisticated ways to try to get around that. But in high dimensions, you always worry, like, have I found all the modes and so on. So typically it's pretty difficult to sample, but here we're not making any such assumption. It's saying that diffusion models can kind of overcome this limitation. And some quick intuition for why this is the case is that we have this forward process, which takes your distribution to Gaussian, and then you slowly kind of reverse time. And so this can be viewed intuitively as some kind of annealing, but you don't have this like slow local mixing. And then the running assumption in this first half of the talk is that the score functions are learned well, and the sense in which they're learned well is that the L2 error is small. And as I'll discuss later, this notion of L2 error makes sense because that is actually the population risk for the score matching objective, which is what we use to actually learn these score functions from data. Anyway, so the result is that if you learn the score functions up to error epsilon, then that translates into TV error at the end, which is also of order epsilon. And also the iteration complexity is a polynomial in all of these various parameters. So pretty good. And then moreover, as I mentioned, like this Lipschitz score assumption can be removed. So one technical device that's used both in practice and in theory is early stopping. So instead of running the reverse diffusion all the way to the final time, you just stop it a little bit early, and then you can completely remove this Lipschitz assumption. And this doesn't hurt you much because if you stop early at some time tau, you only pay logarithmically in 1/tau. But actually, I'm going to show a more refined version of this result anyway. Okay, so this was kind of the original result from a couple of years ago, the first result that gave this kind of polynomial complexity bound for diffusion models, but without making any restrictive data assumptions. So since then, the literature has like really exploded on discretization and diffusion models. I can't really keep up anymore, but I'll try to survey my understanding of the literature today. So this is kind of, I think, one of the best results for these diffusion models recently. So now what happens is we've completely gotten rid of the Lipschitz score assumption. Now there's only a second moment assumption on the data distribution. This allows your data to be lower dimensional or all sorts of crazy things. But now the error metric is changed to the bounded Lipschitz metric rather than TV. This is kind of necessary because if your data distribution is lower dimensional, TV requires you to like exactly find the support, whereas like bounded Lipschitz is a little weaker and allows you to not have to find exactly the support. And then the number of steps now, like there's no Lipschitz constant L, it just becomes d over epsilon. So I think this is a very elegant result, actually. Very minimal assumptions, pretty good result. Okay, so here this theorem gives a bound on the iteration complexity, the number of steps you need in order to run your diffusion model. Now, this is a very important quantity in practice because every iteration of this diffusion model would require you to evaluate the score estimate. And the score estimate in practice is some large neural network, so it'll take time to evaluate. The kind of metric for empirical speed is the number of times you evaluate the neural network, or called the number of function evaluations. We want to make that as small as possible because when you generate an image, you don't want to have to wait a really long time to see your image. So here, like, although the iteration complexity is pretty good, like it's polynomial, it's a very like tame bound, it's still linear in the dimension, which could be pretty slow in high dimension. So we also want to understand not just like, can we get polynomial bounds, but how fast can we go? So there's been a lot of different approaches to try to go beyond this linear dimension dependence. So there's some works, I think Yuting also gave a talk on this on Monday, where you can actually replace the dependence on the ambient dimension with a dependence on some notion of intrinsic dimension, is great. Another orthogonal approach is that instead of running your diffusion models sequentially, there's ways to parallelize it. And when you parallelize it, the sequential depth becomes much, much smaller. But what I'll focus on here is actually a third orthogonal approach, which is instead of discretizing this STE, you can actually move to ODE-based discretizations. And these methods lead to much faster samplers in practice. So what does it mean to do ODE discretization? Well, recall that we have this reverse STE. Turns out there's also a reverse ODE. So here the Brownian motion disappeared and I've changed the coefficient of the score function. Now the fact is, like, although these two processes are different as stochastic processes, for instance, they would have like different correlations, both processes yield the same evolution of the marginal law. And this you could just prove by computing the change of the marginal law. But the point is, like for generative modeling, this is kind of all we care about is the marginal law. Like we don't really care how you got to this image. What we just care about is that the image at the end of the day is distributed according to the correct distribution. So the ODE is also an equally valid way to generate samples. And the reason why we like ODEs is because usually ODEs are much easier to discretize. They just like lead to more regular trajectories.
Sinho?
Yes.
The second one is a deterministic evolution. So marginal of what? So what's the random variable? Not sure I understand.
The initialization is a standard normal. Yeah.
Thanks.
Yeah, so really this is like in the spirit of the previous talk, this is just learning some kind of transport map from the Gaussian to your data distribution, where the transport map is the flow map associated with this ODE. Okay, so in practice, like when we run the ODE, when we want to be able to generate samples in much fewer steps than the SD. So this is widely used in practice for fast generation. And so we want to understand, like, can we actually rigorously say that the ODE is going to lead to better guarantees? Unfortunately, actually, the discretization analysis for pure ODE dynamics is much more complicated than for SD dynamics. Because there's a worry that the errors can accumulate more, and I think this is actually still kind of a problem in the literature. I won't be able to say too much about this, but maybe in one sentence, when you think about the error that you accumulate for these deterministic dynamics, what you would think of is let's try to couple two trajectories, but this ODE system is not actually contractive. So then you worry that the errors can blow up exponentially over time. I guess like we also saw this in Linux talk on propagation of chaos. So that's kind of a very pessimistic argument. In the SDE case, we could do a little bit better using some tools by directly working with the marginal law, but those are not really available for the ODE. Okay, so how did we kind of address this? We came up with kind of like a hack, to be honest. And this hack is you consider the ODE step, which will now be called predictor steps, but you intersperse them with certain SDE steps, and these SDE steps are called corrector steps because they're kind of maybe correcting what the ODE does. And then this like injection of extra noise helps you do analysis, which is a little bit closer to the SDE setting, but you can still hope to see some benefits from the ODE. Okay, so when we first considered this idea of predictor corrector, like to be honest, we just wanted to understand the pure ODE dynamics. That's what we were interested in. But this predictor corrector is not really like new for us. It was actually suggested in one of these papers by Yang Song and his collaborators. So it is a real thing, but it's actually not very realistic. So I will come back to this point because I think this is a very painful point. But anyway, we just wanted to do some analysis. So we also had this work a couple of years ago where we are able to show using this idea of corrector steps that if you do the ODE-based discretization, then, okay, so the assumptions are also like kind of worse than before because now we need like Lipschitz control on the score function and also your estimated score. But these are kind of things that can be removed in later works. But the point is like, if you just look at the dimension dependence, then the ODE can bring some benefits because it gets you past this linear dimension dependence and gets you to square root D. And this was just our attempt of explaining like why the ODE is indeed faster. It's just because you can get better discretization bounds. And then like since this work, there have been many, many more refined analyses of like various ODE discretizations. So here's what I consider to be the state of the art. It's this amazing paper by Yichen Zhao and Gen Li. And their results are the following. Now there's a certain discretization of an ODE-based diffusion model, plus like some like extra corrector steps that gets you like epsilon error, and you have this iteration complexity. Notice that this is a minimum, not a maximum. So if you just take like this last term, for instance, the dimension dependence can be as small as d to the 1/3. And here, like L is some notion of like weak Lipschitz constant that they define. And I do think it is very weak. So for instance, a Gaussian mixture of k components in dimension d, this L would scale like logarithmically in both k and d. So actually like quite weak. I think this is a pretty amazing result that you could push the theory all the way to this level. But one thing that I find unfortunate is that these results are still relying on this idea of like adding artificial noise to analyze the dynamics. And as I mentioned, so this idea of predictor corrector was kind of suggested in this original paper by Yang Song and others. So after we wrote this original paper, I talked to various people working with diffusion models, and then I would ask them like, have you tried these like predictor corrector dynamics? Do they help? And the answer was like a resounding no. This is like never used in practice. And I think it kind of makes sense because if you just want speed, you should just use pure ODE. The correctors are just kind of unnecessary extra function evaluations. And if you want to go for the SDE, and there are good reasons to still stick with the SDE, then you wouldn't be considering this kind of thing at all. So I think this is really a theoretical device that's not reflecting the reality of how diffusion models are actually used. And now, like, one thing I want to do is kind of revisit the SDE samplers. Actually, I kind of want to move away from ODs for this reason. Well, like, it would still be interesting to understand the pure ODE without making too many like assumptions. But okay, let me try to revisit the SDE samplers now. And why do we care about SDE samplers? Is because they're still very widely used. They're still state of the art when you want higher quality. So the general picture I've come to understand is that deterministic samplers like ODEs, they will generate things in much fewer steps. But if you really want more like higher and higher quality, then SDEs are still state of the art. You just run for many steps and SDEs just bring you better quality. Not clear why. Also, like in some areas, the SDE brings you more diversity of samples. So say you want to generate configurations of proteins or something, then you really want to explore the landscape as much as possible. And then the extra diversity from SDEs is very useful. And then finally, there's like these modern approaches to learning to sample via like control theory, and all of these methods still use SDEs. So I wanted to understand, like, can we actually get better guarantees for just pure SDE samplers? And the issue was that in order to get all these refined results for ODE samplers, they're actually using discretizations which are based on randomized midpoints. And technically, it's actually unclear how to take those analyses and apply them to SDE. So the question I'm asking here is like, can we see the benefits of these randomized midpoint discretizations for SDE samplers? Okay, so that brings me to a new result, which is a result for SDE samplers. We show that a discretization of like the pure SDE can get error, which now like if you look at the dimension dependence is also square root d. So this gives you like sublinear dimension dependence for a pure SDE sampler. Okay, and then we have this like again a Lipschitz assumption on the score function, but this Lipschitz bound is allowed to blow up at time 0, so it's actually like not as restrictive. But anyway, hopefully like these assumptions could also be refined in the future. And so this is like a paper that's not quite out yet, but the proof technique is actually based on some like joint works I've been working on with Jason Altschuler. This analysis framework called shifted competition was really necessary for this. Anyway, so at this point, like maybe one question you might have is, why is all this discretization theory like even relevant? Aren't people in practice just going to optimize their step sizes and just like use like whatever works? Like, does this theory really pertain to anything meaningful? So this time around, we actually had some people to implement this, and it was pretty cool to see like visibly how discretization can make a difference. So this is a comparison of just like some standard discretization methods versus randomized midpoint. Like I'm not claiming that we use the power of a small country to test this on super large data sets. I'm just saying like you can actually see a difference sometimes. And this is like comparing the results of different discretization methods with the same number of score evaluations, which is the important metric in practice, 64. Now, one interesting thing is that this randomized midpoint, it uses 2 score evaluations per iteration, which means that the two methods on the left ran for 64 iterations and this one ran for 32 iterations. So despite the fact that it uses more evaluations per step, actually like the discretization is still like good enough to have improvements over just the baseline. And then in practice, like people use this Hoyne sampler actually, and it's quite tricky to beat the Hoyne sampler on image data just because everything's been so like over optimized for image data. And we're still doing some like experiments, but like we can also see some improvements over the Hoyne sampler too in some settings, which is quite surprising. Okay, so that's all I wanted to say about the discretization aspect. Now let me move on to the actual like learning of the score function. Okay, so how do we actually learn the score function? There's this method called score matching, which lets you like reformulate the L2 objective in a certain way. I'm not going to go through the score matching derivation, but the important point is that the true score function, grad log of pt, is the minimizer over all vector fields st of some objective, which I'm just going to call sm sub t. Okay, sm sub t, it takes in a candidate score function st and also a point x0, and then this is the population risk. So it's averaged over x0 drawn from the data distribution. Now this is the formula for SMT, but it's not really relevant for the talk. You could just think of it as the goal is trying to match the score function to the score function of the OU transition density. Anyway, so this is the objective that we try to use to learn the score functions. And then we have data samples from our data distributions. We form the empirical version of this objective, and then we optimize over some class of candidate score functions, usually like parameterized by a neural network. So this is what we train to actually learn these score functions. Now at this point, there's something a little bit weird going on because here I'm now assuming that we have data samples. We have IID samples from the data distribution, and then the goal of generative modeling was to generate a sample from the data distribution. So people in machine learning like to say that generative modeling is the problem of taking samples and generating new samples. So if you ask me, that's kind of nonsense from an information theoretic standpoint. Like if you have like n samples and you use them to generate a new sample, that new sample is dependent on your previous one. It doesn't bring you any extra statistical power. Like you can't do anything new with this new sample that you couldn't with the original ones. So I think that's not the right way to think about generative modeling. Instead, what I would argue is that the right way to think about generative modeling is that you're trying to learn the data distribution, the data from samples. So it's really a problem of distribution learning, and I'll try to clarify that with this slide. So we're going to talk about distribution learning. Let's start with the basics. So what does it really mean to learn a family of distributions given IID samples from a member of this family? So in statistics, we're very familiar with this concept, but if you actually want to do this on your computer, then this problem is still a little bit ill-specified. The reason why is in order to really run this, we need to talk about the representation in which you actually learn the distribution. Because a high-dimensional distribution is a complicated object. You can't just put that onto your laptop. So you need to first figure out how to represent it. And different forms of representation give rise to different forms of distribution learning. So to illustrate, perhaps the simplest setting is suppose that your family of distributions is indexed by a finite dimensional parameter, in which case like you have a parametric family. So we could represent this finite dimensional parameter on your laptop. So then one way to learn the distribution would be just to output an estimate theta hat of this parameter. And this is called parameter recovery. So that's one form of distribution learning. Another form of distribution learning is density estimation, or also in computer science known as the problem of learning an evaluator. So here the goal is to output a function p hat such that p hat is a good estimator of the density at x. And because I'm in this part of the talk, I'm really going to emphasize the computational aspect. Maybe like an even more pedantic computer science way to say this is like, the goal of this learning problem is to output a circuit, p hat, which can be evaluated at any input point and gives you an estimate of the density. And this is like perhaps the most classical way to do distribution learning from a statistical point of view. But there's another way which is actually more relevant to this generative modeling paradigm, and it's called learning a sampler, or also called learning a generator. Now, what is this? This problem is the problem of learning a function g hat, or you should think of this g hat as an algorithm. Okay, the algorithm takes as an input a random seed, which without loss of generality is uniform between 0 and 1. And then it outputs a sample point in RD. Okay, and our notion of closeness will be that the law of the output of our algorithm, conditioned on the data that we already have, should be close to P. Now, let me make a couple comments about this definition in case you haven't seen it before. So first of all, it's important that we condition on the initial data samples, because if I don't condition, then one way to generate a sample would be I take one of my original data samples I was given and I just give it back to you. And that's like a perfect sample from the data distribution, but obviously we haven't learned anything about the distribution. And so it's important to condition on the data and ask like the output of the algorithm, even conditional on this, would be close to P. Because you see, like if I condition on the data and I just give you back one of the original samples, the law of the output would be a point mass at a single point, and that's actually not close to P. So you haven't learned anything. So that's the first comment. The second comment is like, why is this really capturing what we do in diffusion models? Well, think of the learning problem as like we use the data to generate a bunch of score functions. And then these score functions, like if I have this random seed, I could generate all the noise variables and I could use the score functions. And in the end, I get some point out. And that is like the algorithm that we learn for diffusion models. For diffusion models, you could think of learning the algorithm as just learning these score functions. And then the final point I want to make is that although density estimation is a more classical problem, I would argue that this last problem of learning a sampler is more relevant for applications. Because, okay, you give me a density estimator in high dimensions, what am I supposed to do with it? And can I use this to generate a confidence region? Can I use this to estimate expectations of test functions? Depends on how the density estimator is represented, but it's not always easy to tease that information out of a density estimator. Whereas like if I have a algorithm, if I have a distribution in the form of an algorithm that generates samples from it, now I can use these samples to do all sorts of downstream tasks. So in my opinion, this is actually the more relevant problem for distribution learning and what we need to focus on in the future. Okay, so we have these different forms of distribution learning. And one comment is that they're all equivalent information theoretically. Okay, like if I have a density estimator and I have infinite computational budget, then I can just like produce samples from this density estimator by like brute force somehow, right? And then the other way around, if I have a sampling algorithm, then I could learn a density estimator just by generating like infinitely many samples from my sampling algorithm and then just use that to fit whatever density estimator I want. So from an information theoretic lens, these two representations of the distribution, like that's not really a relevant question. But the distinction between these two tasks really comes from computational complexity. Like the reduction from this task to the other is not efficient. Okay, so in this part of the talk, when I try to distinguish between these forms of learning, then we'll have to focus on computational distinctions. So just as an example, if I have a minimax lower bound in statistics, this minimax lower bound would apply to both of these tasks equally well, because this is a purely information theoretic notion. However, if I have a computational lower bound against one of these tasks, which will come up later in the talk, that doesn't necessarily translate to a computational lower bound for the other task. All right, so now with this background in mind, let me kind of revisit the original DDPM result and interpret it in this language. So here's a DDPM theorem. Let script P be nearly any like realistic family of distributions. So this first sentence is capturing the fact that the DDPM results make almost no assumptions about the data distribution. So almost any family is admissible. Second sentence says that the sample complexity of learning a sampler for this family is at most the sample complexity of learning the score functions for this family. Now, this second sentence is capturing the fact that epsilon score error translated to like epsilon total variation error, right? So the sample complexity of learning score function would upper bound the sample complexity of learning the distribution in total variation or bounded Lipschitz metric. And then the final sentence says that the computational complexity is at most a polynomial factor worse between the learning the sampler versus learning the score functions. And this is reflecting the fact that the iteration complexity of diffusion models is polynomial. So the algorithm for generating samples runs in polynomial time. Okay, so all those results I showed in the first part, they are really results about distribution learning that relate the complexity of learning a sampler to the complexity of learning score functions. And a tagline for this could be like learning a sampler, this form of distribution learning is as easy as learning the scores. And yeah, let me just mention there's actually a growing literature on distribution learning in the sense of learning a sampler. And I think like this should be expanded upon. Okay, so in the second part of the talk, what I really want to talk about is this picture. Now, this is what I just told you, is that these prior works on DDPMs, what they're saying is that the task of score estimation reduces to, or sorry, the task of learning a sampler reduces to score estimation. In the sense that if I could solve score estimation, then I can learn a sampler. And now what I want to tell you is that actually these other two forms of distribution learning, parameter recovery and density estimation, can also be reduced to score estimation. This tells us that score estimation is perhaps like a more powerful task than we thought previously, because it enables you to do more forms of distribution learning. But because it's more powerful, it also makes it more vulnerable to lower bounds. If you have a lower bound against any of these branches, you get a lower bound against the task of score estimation. So I will try to make this a little bit more precise. So all of this really comes from some key identity for the likelihood, which I'll explain, and then I'll kind of show you why this implies various things for these other tasks. Okay, so just recap, we have the true score is the minimizer of this like population objective. The score that we learn, well, like we try to solve this empirical objective instead. Now here's the identity. The identity says that the minus log density of my data distribution at any point x0 is exactly equal to the following. I have the integral of this score matching loss, okay, evaluated at the true scores and at this point x0, plus a known constant c, which depends on dimension and the time t that I run the process. The constant is just given here. It's like something related to the differential entropy of the Gaussian, plus a remainder term that vanishes exponentially fast. So if I take the time of the diffusion model to be growing, then this term is usually negligible. Okay, and this identity is not necessarily new. It's kind of present in prior works, but instead, I just want to focus on how to actually apply this one identity. Okay, so let's start with this problem of parameter recovery. So, okay, parametric setting, we have this parametric family indexed by theta, and we have a bunch of samples from, let's say that the model is well specified. Now, like there are various forms of score matching, not just the one that I showed you, like along diffusion models. So a previous paper by Freddie Kohler and Andrei Rustetsky, they studied this like implicit score matching estimator, which is a different variant of score matching. Okay, you minimize some other empirical objective, and then they showed this variant of score matching produces an estimator which is asymptotically normal with some limiting covariance matrix, which I'll call sigma ISM. And then what they were able to show is that if your model satisfies a so-called restricted Poincare inequality, then you can control this asymptotic covariance in terms of the covariance of the MLE, which we usually think of as the best possible. It's the inverse Fisher information. Okay, but if this Poincare inequality does not hold, then actually this this ISM can be much worse than MLE. In fact, like provably so. It can actually be statistically inefficient. What's the story here? The story here is that we have this score matching based estimator, and we're trying to compare its performance to that of the MLE. Whether or not its performance is comparable to the MLE depends on this like restricted Poincare inequality. This is actually part of a broader picture, which I think is pretty interesting and should be like fleshed out a little bit more. And what this picture is trying to do is it's trying to connect the mixing time of certain Markov processes with the statistical efficiency of score matching estimators, which are based on that Markov process. Okay, so every Markov process, there should be associated with it a form of score matching. Okay, and the efficiency of that estimator is kind of related to the mixing time. And the Poincare inequality that I mentioned before, that Poincare inequality is really controlling the mixing time of the Langevin diffusion. So if you have a Poincare, then you have fast mixing, and you also have good statistical efficiency for the score matching estimator. But if you don't have the fast mixing, then you also have poor statistical efficiency. So an example of this is like if your parametric family is like a mixture of two Gaussians and you're trying to learn the weights, this is an example of a distribution where Langevin will mix very slowly because you have to jump between the modes. That's also the same example where the score matching estimator will be inefficient. But there's actually better algorithms for sampling from Gaussian mixtures than just this Langevin. You can do these like parallel tempering or these algorithms that can actually like teleport you between modes. So in this follow-up work, what they did was they considered an algorithm which is more tailored to sampling from Gaussian mixtures. They considered the corresponding score matching objective, and then they showed that the resulting estimator actually gets polynomial sample complexity for learning the parameter of a Gaussian mixture. So this is kind of like furthering this picture of mixing and statistical efficiency. And now what I want to consider is score matching along diffusion models. So diffusion models, they actually always mix rapidly. Because I told you, like, you don't need any assumptions on the data distribution. The diffusion model will always kind of converge fast because of this intuitive annealing picture, right? So does that mean they're always efficient? So what we can do is we can define the DDPM analog of score matching in the parametric setting. So here what we do, this is like very similar to how we learn the score functions in diffusion models. There's one difference though, which is that when we try to learn score functions for diffusion models, we learn a different score function at every single time. Here, because we're in a parametric setting, I'm saying let's learn a single value of the parameter theta that will minimize the score matching loss where all the score functions are enforced to be consistent with the same theta. Okay. So this would be a natural idea of a estimator for the parameter using DDPM. But now, like if you just use this identity that I showed you, I said the minus log density is exactly the integral of this score function, score matching loss, plus a known constant which does not affect the optimization problem, plus a negligible term. So if I kind of forget about these terms, then this estimator that I just defined is actually the same thing as maximum likelihood. So what you can conclude from this is that this negative result, I view it as a negative result because like I was thinking when I first tried to study this, like, oh, we have this cool new estimator inspired by diffusion models, but actually it's just the same thing as MLE. What you can show is that this DDPM estimator also is asymptotically normal, and the asymptotic covariance is the inverse Fisher information under like the usual conditions, like differentiable and quadratic mean and so on. So this says that parameter estimation is as easy as properly learning the scores. And by properly, I mean that all the score functions at every time have to be consistent with a single value of the parameter theta. Okay, so that was one arrow that I showed, is that linking parameter estimation to score estimation. Now let's talk about density estimation. So density estimation is just kind of obvious from this identity. So with here we have a formula for the density. And so a natural estimator to estimate the density would be just to, once we learn the score functions, just plug them in for the right-hand side here. Okay, so if we have a bunch of estimated score functions, our estimate for minus log density would just be the integral of the score matching loss plus this known constant. We drop the negligible term. Okay, so now this theorem is meant to emulate as closely as possible the previous DDPM results, but now for the problem of density estimation rather than learning a sampler. Okay, so what does it say? It says that we can learn some function p hat, which satisfies this guarantee. The expectation of the absolute value of the log ratio is at most epsilon. Okay, using some computational time, which is polynomial. Okay, and these are actually the same assumptions as this very first DDPM result. And then here, like unlike the result for learning a sampler, there's actually some loss when you go from the score error to the error of density estimation. And we like worked pretty hard to make this as good as we could. So we did try to optimize the bound, but this is the best that we are able to get. And then similarly to before, like you can also remove this Lipschitz score assumption if you want via some early stopping. Okay, so this function that you learn, p hat, remember like p hat is really defined here. So p hat is an exponential of something. So that means it's always non-negative, but it's not necessarily going to integrate to 1. Okay, so it's kind of an improper estimator. And this kind of guarantee on the expectation of this log ratio, the way you can interpret it is that it says that on most of your space, you will have a good multiplicative approximation to the true density P. And so this is kind of a weak notion of density estimation. Usual notions are say like L2 risk. So we call this notion pack density estimation in analogy with pack learning. And what we showed is that this task of pack density estimation is as easy as learning the score functions. So here's an application. So let's consider standard like holder class of densities on the interval. You can also extend higher dimensions if you want, but let's stick to 1 dimension for simplicity. S is the smoothness level, and you have some lower bound of the density. Anyway, the point of this class is just like this is a specific class that was studied in a prior work on score estimation. And they were this paper, which is also came out of Yale, obtained some optimal rates for score estimation over this class. And they were able to show that their rates for score estimation, when you combine with the DDPM results, actually gives you a minimax optimal distribution learner in the sense of learning how to generate samples. And now, like with our result, we're able to convert this also into a density estimator. So here's the theorem. There's a density estimator based on DDPM score matching, such that if you consider the L1 risk of this density estimator, it will achieve the minimax rate up to some square root log n factor. But the point is basically like all the previous results in the literature, which are trying to ask how well can you learn distributions using score matching? Before, they're always learning a sampler. Now you can just automatically learn density estimators using our reduction. And in our paper, we also consider some other examples, but just for illustration. And then the last thing I want to talk about is I mentioned that because we now know that score matching can be used to do these extra tasks, that leaves it more vulnerable to lower bounds. So I'll try to talk about some computational lower bounds for score matching. Okay, so as I mentioned, the distinction between these tasks, so we already knew that learning a sampler reduces to score matching. So we want to ask, like, now that we know that density estimation also reduces to score matching, can we prove stronger lower bounds by going through this route rather than the other route? But because the distinction between these two types of learning is only computational, we have to talk about computational lower bounds. Particularly, like, there's a lot of lower bounds in distribution learning, for instance, based on statistical query, or minimax lower bounds, or low degree, but those are all kind of information theoretic in nature. So if you really want to search for a distinction between these two, you have to go to computational lower bounds. And unfortunately, as we know, like lower bounds in computational complexity theory are kind of tricky. But now, like, there have been some recent works establishing like computational lower bounds. they do not start from p does not equal np, because unfortunately, like we cannot do this even in average case complexity. Instead, they start with other well-accepted hardness assumptions. So typically, we use notions of cryptographic hardness, which say that solving a certain learning problem is as hard as breaking some crypto system. Okay, and that's pretty good evidence, because that would say, like, if you could solve this learning problem, then you could break this crypto system, which a lot of people think is secure and have thought about for a long time. So that's good evidence for hardness. And indeed, there have been some cryptographic hardness problems which have been proven for density estimation tasks. But these cryptographic lower bounds actually do not apply to the problem of learning a sampler. So I think this is an interesting open question, is to get cryptographic hardness for this learning a sampler problem. And I could talk about it more offline if you're interested, but it's kind of fundamental, because like cryptographic hardness usually starts with the assumption that no matter how many polynomially many samples I draw from these two distributions, I cannot tell which one is the planted distribution. Learning a sampler would just let you draw more samples, but then we kind of already had access to this when we're trying to break the crypto system. So actually, this is kind of a subtle question. But anyway, because like we know some cryptographic hardness for density estimation, now we could try to port this over to score estimation. So yeah, let me mention there was this prior work by Min-Jae Song, who was at NYU, and he proved cryptographic hardness for learning score functions for Gaussian mixtures. We're just going to recover his result at the end of the day, but the point is, like, his result was based on this very like tailored argument, and now like through this reduction, you kind of see the general picture. The general picture is for any family P, if you know that it's cryptographically hard to do density estimation, you just have to apply our reduction. Therefore, the conclusion is that learning the scores is as hard as this notion of density estimation. Okay, so when you apply this to Gaussian mixtures, you're able to get this theorem. It says that for any positive epsilon, it's cryptographically hard to learn the score functions of mixtures of Gaussians with d to the epsilon components in dimension d. So as soon as the number of components is growing with the dimension, it's cryptographically hard. And if you're curious about the chain of reductions, like, so our work was saying that score estimation is as hard as this density estimation. And then due to these works, it's known that density estimation for mixtures of Gaussians is as hard as this continuous version of learning with errors, which can be reduced to the original learning with errors, which can be reduced to certain like worst case lattice problems. And these lattice problems are actually thought to be secure even in a post-quantum world. So that's pretty like nice notion of hardness. It says that if we could learn these score functions, we could break one of our most promising candidates for post-quantum cryptography. Okay, so I think that's all I wanted to talk about. This is the summary.